So here they say on 13 May 2021, Mars and Earth were 3.171 times 10 to the power 11 meters away from each other's surfaces. All right. Mars has a mass of 6.4 times 10 to the power 23 kg. Of course, there's 17 there. And it has a radius of 3.4 times 10 to the power 6 meters. The Earth has a mass of 5.98 times 10 to the power 24 kilograms, and it has a radius of 6.38 times 10 to the power 6 meters. All right. Then the question to us here is, please state Newton's law of universal gravitation. And after stating this law, then the next one says, please calculate the force of attraction between the mass and the Earth. And here they say to you, well, this is simply for 4 marks, okay? Now that's fine. Now, the most important one in this case is actually the distance, all right? Now, what is the distance going to be if we look at it very much carefully? They didn't give us the distance between the centers of the Earth and the Mars, no. But instead, they gave us the distance between the surfaces of the Earth and the Mars. So in other words, we need to take this 3.171 times 10 to the 11 meters, and we need to add it to the radius of the Earth as well as to the radius of the Mars. Do you see that? So that we can get the distance between the centers of these two planets. Just to make a much more clearer scenario for you, this is what we are having. Well, this is our beautiful planet, which is the only one that supports life. And this is also the Mars, all right? That's fine. Now, when we state the law of universal gravitation, we say this gravitational force is inversely proportional to the square of the distance between their centers. And listen to yourself as you say it. But now here, we are only given the distance between the surfaces of these two planets. So it stands to reason that we need to add this distance to the radius of the Earth as well as to the radius of the planet Mars. I think it's much clearer now, all right? So let's go ahead and do that. So we simply come and say, okay, fine. The gravitational force between these two is just going to be equal to Gm1, m2, and this is divided by r squared. You can say r squared or you can say d squared. I think in this case, it's appropriate to say d squared, but it doesn't matter, right? No, it doesn't matter at all. Okay, so now we say, well, the universal gravitational constant is 6.67 exponent negative 11. The mass of the Earth is this much. And the mass of the planet Mars is given to us as 6.417 times 10 to the power 23. And then we say this entire thing is divided by the distance between the square of the distance between their centers, right? Now we take the radius of the Earth and we add it to the radius of the planet Mars. And we further add this to the distance between them. This is the distance between them, not the distance between their centers. There is a difference. In electrostatics, as you'll discover later, we'll be focusing on the distance between them, not their centers. All right? So let's see how much do we get when we plug everything into our calculator. So we have 6.67 times 10 to the negative 11, and this is multiplied by this much, and this is multiplied by this much, all right? Okay. And this is divided by 6.38 exponent 6 and added to 3.4 exponent 6 and further added to 3.171 exponent 11. All right. Yes, what am I doing here? It's supposed to be 11 and everything must be squared. So if you plug everything into your calculator, you find that this gravitational force will be equal to 2.55 times 10 to the power 15. And then you say newtons. It's a very great force, or a large force if you like. I'm not sure. But this should be the magnitude of the gravitational force between these two planets. All right. Now 4.3 they say perseverance, a car-sized mass. What is this? A car-sized Mars rover. It enters the Martian atmosphere. Okay. I don't know what is a rover. Now they say to us, calculate the acceleration due to gravity on the Mars. Maybe let's assume that this Perseverance is a spaceship or whatever. I don't know. But we know that it is an object that has mass, right? Because they say to us it is car-sized and it enters the atmosphere of the planet Mars. Now they say calculate the acceleration due to gravity on the surface of the planet Mars. And here, if you can see well, you can see that they didn't give you the mass of this car-sized Perseverance, right? That is because the gravitational acceleration of a planet, it does not depend on the mass of an object. No, it only depends on what am I saying? I want to say it only depends on the mass of the planet, as well as the radius of that planet. So that's what you need to know, okay? And this is the formula for the gravitational acceleration. You say G is equal to Gm divided by r squared. Okay? And this is actually derived from the formula that says Fg is equal to Fg. What is the meaning of this? You can define mg in terms of the equation mass times the acceleration, or you can define Fg in terms of g times the mass of the Earth or whatever planet times the mass of an object that is on that planet, and this is divided by r squared. Now, this mass will cancel out with that mass. If, of course, you were trying to do your cross multiplications and things like that. So that's how we got G equals Gm over r squared. It comes from the fact that whether you calculate the gravitational force using mg or you use the universal law, the answer will still be the same. But then since the mass occurs on two sides of the equal sign, then they can cancel out. Okay. The universal gravitational constant is the same throughout, whether you are on the Earth or you are on Mars or whatever planet that you choose. Otherwise, it wouldn't be called universal, right? Then here they said to us the mass of the planet Mars is given to us as 6.417 times 10 to the power 23 kilometers. No, meters. No, mass, it's kilograms. Eish, it's bad. And then we say this is divided by the radius of Mars, which is just 3.4 times 10 to the power 6 meters. And of course, we need to square this. So let's see how much do we get if we press this into our very nice calculator. All right. Well, let's see. Of course, we want to see. Otherwise, what's the point? Seems like I need to work on my calculator speed. Okay. Wait, why am I getting maths error? It's 6.67 exponent 11, yes, times 6.417 times 10 to the power 23, yes, and this is divided by 3.4 times 10 to the power 6 meters, yes. It's supposed to be squared. Guys, I'm getting a maths error here. But if you press this into your calculator, it's supposed to give you 3.70. And then, of course, the gravitational acceleration, its unit is just going to be meters per second squared, because the object is accelerating due to gravity. Well, here they say to us, how does the acceleration calculated in the previous question change as perseverance gets closer to the surface? Right only increases, decreases, or remains the same? And then they say, explain your answer to that question. Okay, so let's try to make a sketch, a representation of the situation. So let's say this is the planet Mars here. And let's say we have a spaceship that is headed to Mars. All right. Okay, this is our spaceship. Now let's say this spaceship is going to enter the surface of Mars, or rather the atmosphere, and then it keeps on getting closer and closer to the surface. Now they want to know, how will the gravitational acceleration change as this object gets closer and closer to the surface? Well, you'll simply tell them it's going to remain the same. Why? Because the gravitational acceleration is independent of the mass of this object. It doesn't depend on the mass of that object whatsoever. So whether the object is there or the object is not there, the gravitational acceleration will be 3.70. So that's the reason. It doesn't depend on the mass of this object.